this is how we've just rewritten the group law. So sometimes we just write J for some arbitrary group element, and sometimes we want to enumerate the group elements. So Gj is the jth group element. And we write it like this. We write the multiplication as a sum over all group elements. And then, of course, there has to be a coefficient here picking just one term in this sum. So for fixed G and fixed J, this capital R here has to be non-zero for just one term in this sum, because we know when we multiply two group elements, we get just one group element. And now these R's here as matrices, order of the group times order of the group matrices, they define a representation of the group on its own algebra. And how can we see this? Say we take two group elements, G and H, and then the product is some other group element, G prime. Let's write this in this way as we've written it above in terms of these R's. So GH applied to GJ is just sum k from 1 to the order of the group. We copy the H and then we write GK R of H index Kj. Just the same way as we did up here. And now we do it again for G times Gk here. So we have the sum, let's say L from 1 to the order of the group, and we copy the sum K from 1 to the order of the group. And now we have GL R of G index LK R of H index Kj. So the pink part here became the sum of L and these terms here, also just as defined up here. Now let's compare this to what happens when we apply just the G prime to a Gj. Then we get, say, sum L from 1 to the order of the group, GL R of G prime index Lj. And now let's compare. There is a sum over L and the GL in here in both terms. And when we look at the rest, there is here a matrix product, and here's the component of a matrix. So the pink part really just says R of G times R of H is R of G prime. So we really have a representation, and if you look at how the identity is represented, then you see that it's the unit matrix. So it's really a representation.